Hello and welcome to our first lesson of Chapter 4. This is section 4.1, talking about maximum and minimum values. We're going to be looking at how derivatives affect the shape of a graph of a function and how they help us locate maximum and minimum values. We're then going to use this to figure out optimization problems later in the chapter. The maximum and minimum values of a function are called extreme values. There are different types of these. There's an absolute maximum, which is the highest point in the domain. This is also called a global maximum. There is an absolute minimum, which is the lowest point in the domain, also called a global minimum. Then we also have local maximums and minimums, or relative maximums and minimums. These are points that are higher or lower than the points on either side of it, but they are not the lowest point in the domain or the highest point in the domain. So a local maximum or minimum could also be absolute. Okay, we're going to take a look at an example here. If we look at this curve, we're going to label all of the absolute and local maximum and minimum points on the graph below. So the absolute minimum and absolute maximum are the highest points you see anywhere on the graph. So this one here would be our absolute maximum. And this one here would be our absolute minimum. The first one that we just did is the highest point anywhere on the curve, and the second one is the lowest point anywhere on the curve. Now we have a couple other points here, 1, 2, and 3, that are higher or lower relative to the points around it. This first one we drew in the middle is part of a valley or a minimum part of the curve, but it is not the lowest overall. So this would be a local minimum or a relative minimum. Okay. Same with the farthest right point. This is lower than all the other points around it, but it is not the lowest on the graph. So this is another local minimum. And the middle red point I've got here would be a local maximum because relative to the points around it, it is higher, but it is not the highest on the graph. Now, a local maximum or minimum may occur in the following cases. And so if I had a curve, we could draw tangent lines to this local max and local min, and the slopes of these tangent lines would be 0. So when it says the slope is 0, this means the slope of the tangent line. So the slope of the tangent line at that part of the curve should be 0 if we have a max or a min. So this function we just drew was f of x. So this is also saying f prime of x would be 0 at our maximums or minimums. The other way I could have this is for the slope of the tangent to be undefined. And that would be something like, for example, if I had a corner, okay, this has a maximum here, but I actually don't have an f prime, right? We know from previous chapters that we have for a corner an undefined slope of our tangent line. We can't actually find f prime here. So this would be f prime is undefined. Again, we can't draw a tangent line there. In other words, the points where f prime of x equals to 0 or f prime of x does not exist, those are what we're looking for. Those are called critical points of the function. And the x-coordinates of the critical points are called critical numbers. If f has a local max or min, it must occur at a critical point. However, not all critical points are local maximums or minimums. So an example of where that might happen, where we have a critical point, but we don't have a maximum or a minimum, is something like this. What if f of x is equal to x cubed? Well, then f prime would be 3x squared. And so what we'd be looking for is where does f prime equal 0 or not exist? Well, f prime equals 0 if 3x squared equals 0 or if x equals 0. This means that I have a critical point at the origin. Okay. However, we can see that that is not a maximum or a minimum for this function. Okay, so even though we have a critical point, we do not have a max or a min here. However, if we have it a max or a min, it must happen at a critical point. The other thing we would check would be, where does f prime not exist? And the answer here is never. Right? F prime is 3x squared. 3x squared exists for any x value. So let's try a couple questions, not a couple numbers, a couple questions. We're going to determine the critical numbers of each of the following. So to determine the critical numbers, we need to find f prime. And then we need to check and see, where does f prime equal 0 or does not exist? So we're going to find the x values where f prime equals 0 or f prime does not exist. Okay. So for this first one, y prime would be 6x squared minus 6x. Okay. Or you can factor and say 6x times x minus 1. So if I want to find where does y prime equal 0, this means that you'd have to have 0 equals 6x times x minus 1, which would mean x either equals 0 or 1. And then if we look for where does y prime not exist, my arrow's on the wrong side here, where does y prime does not exist, this would never happen. Y prime exists for all real numbers. So this means my critical numbers are x equals 0 and 1. Now, if you'd like, you can pause the video here and go ahead and try B on your own. If you're not quite sure yet what you're doing, you can keep watching. So we're going to start by finding f prime. So we'd have 4 over 3 x to the 1 over 3 minus 1 over 3 x to the negative 2 over 3. Probably a good idea to rewrite this as 4x to the 1/3 over 3 minus 1 over 3x to the 2/3. Now, in order to be able to find where does f prime equal 0 nicely, it's probably a good idea to rewrite this as one fraction. So this would give us 4x minus 1 over 3x to the 2/3. And how we would get there is the left-hand fraction needs some extra x's. I'd need to multiply by x to the 2/3 over x to the 2/3. When I do that, I get 4x on the top and 3x to the 2/3 on the bottom. So this is my f prime. Now I'd have f prime equals 0 if 4x minus 1 equals 0, or x is equal to 1 over 4. And f prime does not exist if the denominator is 0. So if 3x to the 2 over 3 equals 0, or if x is equal to 0. So my critical numbers would be x is equal to 1 over 4 and x is equal to 0. Now the last part of this lesson is the extreme value theorem. Now, as with most of our other theorems, it sort of sounds overwhelming when you first look at it, but when you actually get into it, it's it makes some sense, and it seems a little bit more reasonable if you put it in layman's terms. So the actual theorem is if f of x is continuous on the closed interval a to b, then f of x attains an absolute maximum f of c and an absolute minimum f of d at some numbers c and d in our interval ab. What this is saying is if we have f is continuous, I'm going to fix that and not make so many of the same values. Let's do something like this. Okay. F of x is continuous, and we're going to start at some a and end at some b. Okay. So this would be f of a and f of b. Okay. So we're continuous on our closed interval. It's saying then f of x attains an absolute maximum. What this is saying is you've got to have a highest point somewhere. And this has to be true if I'm drawing the entire curve without picking my pen up off the page. If I had something like a jump or an asymptote where you have your function going off to infinity or negative infinity, you wouldn't have an absolute maximum or minimum because they might be infinity. But if I have a closed interval and continuous between our endpoints, we must have somewhere in that interval a largest value and somewhere in that interval a smallest value. So here, if I figure out where does my largest value look like it is, well, it looks like it's probably about here. So that would be my f of c, and this would be my c. And where does it look like my smallest value is? Probably here. This would be the d value from the theorem, and my f of d would be over here. So again, it's just saying that on a closed interval, you have to have a biggest and a smallest points. Now, the example we just drew, we have two extra points. We could have that the smallest point or the largest point is one of our endpoints. And something like that might look like this. Okay. If I start at some a to b, that means the only part of my function I'm actually considering is this right here. Okay, I'm starting at a and I'm ending at b. Now, if I think about this function, where is the highest point? Well, my highest point is here. So that makes this my c value. That is my highest point. And where is my lowest point? My lowest point is here. That makes this my d value. And my f of d would be here. So I could have my absolute maximum or my absolute minimum be inside the function, like this first example, and be two extra points that are not the endpoints, or it could be at the endpoints. If I think about my tangent lines here, in my first example, if I drew a tangent line at C, it would be horizontal and its slope would be 0. At D, it would be horizontal and its slope would be 0. Therefore, my f prime would be 0. So what I'm really looking for using my extreme value theorem is critical points or endpoints. Okay? So the absolute extrema of a continuous function on a closed interval occur at the critical points or at the endpoints. But there has to be an absolute maximum and an absolute minimum on a closed interval of a continuous function. So if I wanted to actually try an example, the first thing is we have to be continuous. So in my example, f of x is a polynomial. This means it's continuous. I have a closed interval. 1, -1 is my a, and b is my 4. Okay. If I want to find my absolute maximum and minimum, I need to find where does f prime equal 0 or f prime does not exist. And then I'm going to actually plug those x values and my endpoints into my original function and see which one's biggest and which one's smallest. So if f of x is equal to x cubed plus 3x squared plus 4, f prime of x would be 3x squared plus 6x, okay, or 3x times x plus 2. This exists everywhere, but it equals 0 if x equals 0 or negative 2. Now, I'm not going to use the negative 2 because it's not in my interval. So I'm only going to use x equals 0. Okay? If I want to know the absolute maximum and minimum, I need to find what is f of 0. And then I also need to test the endpoints, f of negative 1 and f of 4. The biggest y value I get here, remember f of something is just the y value on that polynomial. So the first one is the y value of the polynomial when x is 0. I'm going to plug 0 in, get 0 plus 0 plus 4. So 4. So my y value on my polynomial when x is 0 is 4. My y value on my polynomial when x is negative 1, we're going to plug negative 1 in. And we get 3 plus 4 is 7 minus 1, we get 6. So this is bigger than 4. So we know that the 4 is not our maximum. And then I'm going to try 4. I get 4 cubed plus 3 times 4 squared plus 4. That's going to be a big number. Okay, we get 116 there if we plug that in. So we can see 116 is my biggest number. So this has got to be my maximum. 4 is my smallest number. So this is my minimum. So we're going to have, that means our absolute max is at 4, 116. That would be the point where our maximum is. And our absolute minimum is at 0, 4, the point where our minimum is. So hopefully we can see we tested for where does f prime equal 0 or does not exist. Once we have those x values, we're going to plug them into our original function, plug the endpoints into our original function, and find the biggest and smallest numbers. Okay, biggest ones are max, smallest ones are min. And that is it for 4.1.